is by far the most difficult question you guys have had. So if you got trouble with this, don't feel discouraged. This is a pretty difficult question.
Okay, I'm actually going to move this out of the way so that we can read the.
Oh, yeah? Sorry.
No, not at all, not at all. Right. So, and in fact, I'll request you to turn around slightly so that they read everything. Okay.
Where am I going?
No, now you're good. Now you're good. So you have two. Draw pictures. Pictures are good. Okay. So there's a star A and a star B. And they're basically going around their common center of mass. Okay? And they're telling you that the period is 50 years and the distance between them is 20 AU. Okay? Star B is observed to be 2.2 times as far from the center of mass as star A. Okay, so if this is 1 unit, then this is 2.2 units. Yeah, that's what it says. Okay, so definition of center of mass, MA RA equals MB RB. And I told you that RB is 2.2 times RA. Okay, RB equals 2.2 RA. And therefore you will get MA equals 2.2 MB. That's the first step. Is that making sense? This is just center of mass. Center of mass definition, MA times RA equals MB times RB. RB is 2.2 times RA and therefore MA equals 2.2 times MB. Okay. Now coming back to Newton's form of Kepler's third law. Can I write this stuff out? Or Deanne, can I get rid of this stuff? Okay, I'll just leave it there. Right. So Newton's form of Kepler's law, MA plus MB times P squared equals RA plus RB the whole cube. Right? That's Newton's form of Kepler's law. True or false? Yes, yeah? Okay. And what have they told you? What have they asked for? They have asked for the masses of the two stars. So what they're asking for is basically something related to this. Okay. So let me call MA plus MB, the total combined mass of the two. Let me just call it M. Okay. So this tells me the total mass times PQ, P squared equals RA plus RB is that separation, the distance between the two stars, right? Equals R cube. So M equals R cube divided by P squared. Okay. And we are working in solar masses, AU and years. Okay. So what is M? M is in terms of AU, it is 2,000, sorry, 8,000. Okay, why 8,000? That's R cubed in AU. Okay, so that's 8,000 divided by 50 squared, which is 2500. Hey, have I got the other way around? Equals how much?
Yeah, equals 3.2. Well, m is 3.2 m
Yeah.
a, right? So
Equals how much?
I missed you.
3.2. And this, of course, the units are solar masses. Right? When you work like this, the units are solar masses. Right? And we know that one of the stars is 2.2 times the mass of the other star. So what are the masses of the two stars? And the two of them together are 3.2 solar masses. So they are how much and how much? 1 solar mass and 2.2 solar masses. Making sense? Yes? Okay. Very clearly, you folks need a 5-minute break. So take a 5-minute break.
eat some of the sugar.
Eat something.
So we need to talk about parallax. And so I think it's worthwhile to illustrate parallax before we actually go through and do it. So I always like to use the example of your thumb, right? Hold your thumb out and close one of your eyes and line it up with something in the distance. So like something on the wall, something far from you, right? I mean, you guys could probably just do this since, okay, if you don't want to, but this, what basically what you see is, well, why don't you try this? Yes, okay, there we go. Now close one of your eyes, right? And line it up with something in the background. Now switch it, right? And you see that your thumb moves with respect to the background. Now, the question is, what do you think is going to happen if you move your thumb closer to your face? Is it going to move more or less with respect to the background? I mean, you just try it if you want, if you're not certain. Like, what do you think, Ian? Well, give it a shot. Why don't you try it? Put your thumb closer and try it. Yeah, right. And I think that's it's important to understand that parallax works for objects that are nearby, stars. I mean, that's what we mostly use it for, is to measure distances to stars. It only works for nearby objects because the further you move away, the less that shift that we saw becomes. And the smaller it becomes, the harder it gets to measure. There's a nice little animation I wanted to show you guys. Hopefully I haven't closed it. So this kind of animates exactly what we're doing when we measure parallax. Can you all see that? So this demonstrates what you just noticed, right? If the star is closer, the distance it appears to move, just like your thumb when it was closer, is larger. And there's a mathematical relation. I'd actually like for you guys to derive that mathematical equation, if you can. So just give it a shot right here. Here's using these definitions for all the terms. What is D in terms of pi and r? Where pi is this angle, and r is this distance.
Is pi constant or variable?
It's constant in this drawing here.
Yeah.
And I would remind you to think about trigonometry and right triangles. So you guys should get something like this, right? The tangent of this angle, the tangent of this angle is equal to the radius divided by the distance, right? That's the definition of tangent. And this angle, pi, is half of this theta. This is actually what you observe in the sky, right? When your thumb is moving, that's what you're observing. That distance is this pi, this angle, or this theta. So pi is theta divided by 2. And then a simple identity, tangent times pi, or tangent of an angle that's very small is just equal to that angle, basically.
So guys, he's using pi, instead of calling it x, he's calling it pi. This is not pi radians. Okay?
Yes, I'm really sorry. The manual, thank you for pointing that out. The manual the drawing I'm using had this already defined. It's a silly definition because pi everyone thinks is 3.14. Here it's just an arbitrary angle. That's what you were asking, is it constant, I think is what you meant, right?
Think of it as x or something.
Yeah. Think of it as x or theta would be better. That's the way. But here we but so just so you're clear, it's not pi as in 3.1415, whatever. So this identity, if the angle is small, is the tangent of the small angle is just that angle. When that angle is measured in radians, that has to be clear. You have to measure in radians. And so you get this. The distance equals the radius divided by pi. This is the crucial equation. You can call it beta or whatever you want. This is the equation you need to remember. And this is the equation you need to write down. So the distance to an object is measured in parsecs when the angle is measured in arc seconds. Okay? And arc second is defined as 1/3600th of a degree. Okay? And it ends up being something like 400,000 arc seconds in a radian. The actual conversion you guys can look up. I should have provided it here, but for now you don't need to because you're never going to get an angle measure in radians. You're always going to get it in degrees. Okay? Or I'm sorry, in arc seconds. So okay, now there's some few parallax questions that we should talk about. This equation is fairly simple, but there is some conceptual basis for it. So hopefully these questions will focus on some of the concepts. So just make sure you guys can do these questions. Go ahead and try.
Do you folks have this piece of paper? Okay, because this will be useful to you for today's problem.
Yeah, I think that has all the concepts.